Hello, friends. Parker here, and this is ParkerZen. Tonight we're winding down with the brilliant voice and insights of Professor Brian Cox as I help guide you toward a peaceful, restful sleep while we explore such things as the mysteries of time and space, black holes, and relativity. This video is a sleep-focused remix featuring the calm, reflective voice of Brian Cox, completely reworked to provide a slow, meditative experience with calming audio and visual effects we've created to help you unwind and drift off with ease. So take this time to let go of the day, forget about the world, and let's see which of us falls asleep first, you or me, while listening to Brian Cox explain the secrets hidden inside black holes and the mysteries of the universe. Let's begin.
I've been doing some work on black holes recently, which I hadn't started last time I saw you, actually. So I got interested in it. And the amount of the progress that's been made in trying to understand how they work. And a question that was posed by Stephen Hawking a long time ago, really 1970s, early 1980s, which is what happens to stuff that falls in. But the simplest question you could possibly ask. There's progress being made on that now, which I think is profound and exciting. So in 1916, a man called Carl Schwarzschild remarkably managed to solve the equations for a perfectly spherical, non-spinning ball of matter. It's the simplest thing you could do, which tells you how space and time are distorted by it. And that's a model for a star. It's the simplest thing you could do. So he solved the equations. It's a remarkable thing. In those equations, there is a description of a black hole, although it wasn't realized at the time. So it's a remarkable piece, simple piece of mathematics, actually. So essentially, what's the idea behind a black hole? One way to think about it is that you could you remove the star from this fabric, but leave the distortion behind? So if you do that, you get the description of a black hole. But you might say, what do you mean? How can that be formed in nature? So you think about what a star is. Then a star is a balancing act. So it's a mainly hydrogen and helium collapsing under its own gravity. That's how our sun formed 4.5 billion years ago. So it's collapsing. So what stops it collapsing? Well, as it collapses, the core heats up, and that initiates nuclear fusion reactions in the core. In the case of our sun, it's hydrogen being fused into helium. That releases energy, which creates a pressure which holds the thing up. So it's balancing, but it needs the fuel. And it's not infinitely big, of course, so at some point it runs out of nuclear fuel. And ultimately, no more fusion reactions can occur in any star. And so the star will resume its collapse. So the question is, well, is there something that stops it? Because if there isn't something that stops the collapse, then it will collapse without limit. And so actually, if you look at the history of physics in the 20s and 30s, people were saying, well, we'd like to avoid this idea that the thing will collapse without limit, because if it does, then Schwarzschild's equation predicts some very strange things indeed. And so people kind of try to avoid it. It was really actually Oppenheimer and his student Schneider in the late 30s, just before the Second World War, that showed that really, with some assumptions, it looks like a massive enough star could actually collapse without limit. So what does that mean? Collapses without limit. It means that essentially it does what I said. You essentially remove the star from the fabric of the universe, leaving the distortion behind. So a black hole, it's interesting that the idea, or the first glimpse of them theoretically, came very shortly after Einstein's theory of gravity was published in 1915. Although it wasn't recognized as such at the time, this glimpse. Essentially, what does Einstein's theory do? It's important for what follows. It's a theory of space and time, and how space-time, which is often described as the fabric of the universe, responds, or warps or curves, to matter and energy in the universe. So the equations, basically the theory that Einstein published all those years ago, will say, give me some distribution of matter, something like a ball of matter, and the equations will tell you how the fabric of the universe is distorted. And by the way, the force of gravity in that theory then is the response of everything else in the universe to that distortion. So Einstein would say, what are we feeling now? Newton would say it's a force between us and the Earth. But Einstein would say there isn't a force. What we're responding to the distortion in the fabric of the universe created by the Earth. So that's John Wheeler, actually, the great physicist, put it beautifully. He said, matter tells space-time how to curve, and space-time tells matter how to move. It's mainly theoretical, although we have now got photographs of them. So we have two photographs, which are radio telescope photographs. One of the one in the centre of our galaxy, which is a little one. It's called Sagittarius A star. It's a little supermassive black hole. So it's about 6 million times the mass of the Sun. The first photo that was taken, it's a collaboration called Event Horizon, and they took a photo of one in the galaxy M87, 55 million light years away. That thing is around 6 billion times the mass of the Sun. I mean, imagine that, 6,000 million times more massive than our Sun. There are bigger ones than that, but that's that's the scale of them. It's a big-ish one, that. But if you think about it, I mean, so there's a number. It's called the Schwarzschild radius of the thing. So if you took our Sun, which you can fit 1 million Earths inside, and collapsed it down to make a black hole, it would form a black hole when it shrunk within a radius of 3 kilometres, about 2 miles. So you've got to take this thing, about 500,000 miles radius or something like that, the Sun. So you squash it down till it's about 2 miles, and then that would form a black hole. 6 billion times the mass of the Sun means you multiply that by 6 billion. So these things, the so-called Schwarzschild radius is larger than our solar system, basically. And the black hole, the idea behind the black hole is, let's say you take the Sun, a star the mass of the Sun, and you just collapse it, and you keep on collapsing it. You get to a point when the radius of the Sun is not 700,000 kilometers, which is what it is in miles, 500,000 miles, and you squash it down, and you squash it until its radius becomes 3 kilometers. 3. Then there are several ways to look at this. One is that on the surface, the speed you'd have to travel to escape its gravitational pull, it's called the escape velocity, would exceed the speed of light. That's one way to think about it. So even light rays emitted from the surface, if you could squash it down that far, would just stay there. They would not escape, because they'd be trying to go at the speed of light, and the escape velocity is the speed of light, and they just stop. So what happens then if a star collapses inside that number, which for the mass of the Sun, 3 kilometers, is called the Schwarzschild radius? Then it will collapse without limit. Nothing will stop it. And so all you will get is essentially the geometry of space and time, the curvature. And that's a black hole. So what you're seeing there is the emission from the material that's swirling around it. It's called the accretion disk. So you have material that's orbiting very fast, emitting a lot of radiation, and that's what you see. It's a flat disk, by the way. So you think Saturn's rings. So this material is very flat. But what you're seeing in that photograph is the light rays being bent around the black hole from that flat disk. So that was a prediction from Einstein's theory, basically. He published it in 1915. And you can predict that that's what one should look like. And then just about, what was that, 4 years ago now, maybe 5 years ago, for the first time in history, we get an image of one, and it looks like the prediction. So here, the light, you might say, what is the light in this picture? By the Event Horizon Telescope. So it's not from the black hole, because as we've just said, black holes trap light. It's from what's called the accretion disk around the black hole. So you're to imagine really material spiraling around in orbit around this very dense object, and very violently orbiting. And so it heats up and it emits light. So imagine a flat, thin disk of material around the black hole. But this does not look like that. What you're seeing is the distortion, the curvature of the light rays. Because we said that you might think, well, light travels in straight lines. But Einstein's theory says that in the vicinity of this thing, the fabric of the universe itself is distorted. So the light, the paths of the light rays follow the distortion. So what you're seeing, this famous image of a black hole, like if you think of the film Interstellar, that code, by the way, is an implementation of Einstein's equations. Kip Thorne and others helped them do that. So it's really a prediction. So what you're seeing, so imagine this disk of material around this thing, like picture in your mind's eye Saturn. Then light rays, let's say from your perspective, from behind the black hole, on the, let's say that on the disk, go around into your eyes. Sometimes they orbit and then go around into your eyes. And they go into your eyes from every point on the disk, from underneath and at the top and behind. So you have light rays going around this thing. So you see that. That's what you see as an image. So there's a prediction of Einstein's theory, which is a real black hole should look like that. It's the characteristic donut shape that you see. Well, here's an image with radio telescopes of such a thing. And it looks like the prediction. It is a bit blurry. This was actually the second one that was imaged. The first one was in a galaxy called M87, which is 55 million light years away and is bigger than this one. Bigger, which I mean, so this one's about 6 million times the mass of the sun, give or take. The one in M87, 6 billion times the mass of the sun. So this is the baby supermassive black hole. I think I'm right in saying we don't fully understand why all galaxies, maybe there's an exception, but all galaxies have a black hole, a supermassive black hole in the centre. It's obviously got something to do with the way they form. And one of the purposes, by the way, of the James Webb Space Telescope is to try to look at the formation of the first galaxies. So that's one of the reasons that telescope is up there. So it's cutting edge research. We're trying to understand how the galaxies form. But I clearly, you're right, that it has something to do with the way the galaxies form. They do pull in material. If you've got stuff orbiting around them, it stays orbiting around it. The way we first detected the one in the Milky Way, before we could, because that image is very new that we have of it, is the stars orbiting it, very close to it. They're called the S stars that whiz around in these orbits very close to the black hole. We think that, I would say all galaxies, maybe there's an exception or so, but pretty much all galaxies have supermassive black holes at their centres. We don't quite know why, actually. We don't quite know how galaxies form in the early universe. It's one of the things that the JWST, the James Webb, is looking at in some detail, the new space telescope. But to good approximation, all galaxies have these things. And they can be different masses. So, as I said, the M87 galaxy has one that's 6 billion times the mass rather than 6 million times the mass. So, but how big is it? So the number I always remember in my mind is the Schwarzschild radius of the sun, which is, as we mentioned, it's the radius you'd have to squash the sun down to make a black hole, and it's 3 kilometers. So it goes like the mass, so you can work it out. So if that's 6 million times the mass of the sun, then the Schwarzschild radius is 6 million times 3 kilometers. Mm-hmm. So it's kind of easy to do the math, actually. So that would be you might call it, you have to be careful with your language, but let's say that this thing it gives you an idea of the size of this structure. So the disk is outside it is much bigger. There's an experiment called LIGO, which is what it stands for, something like gravitational interferometer. I can't remember exactly what but so basically it's laser beams, and there's one in Washington State, north of Seattle, and one in Louisiana, and they're kind of laser beams, 4 kilometer long laser beams at right angles, and they can detect these very tiny shifts in effectively, you could say the length of the laser beam. It's a bit more fiddly and complicated, but it essentially measures the distortion in space-time. And it's way less than the diameter of an atomic nucleus, by the way, way less. And so we've got data now of the collision of black holes and those event horizon pictures with radio telescopes. So that's part of it. But the main bit has been theoretical advances in understanding exactly it. In a sense, it was what's wrong with Stephen Hawking's calculation, which is a weird thing to say sometimes because people think Stephen Hawking get his math wrong, but he did actually in his So what he calculated back in 1973, 1974 is that a black hole, so we picture this thing from which nothing can escape, even light. So when you go in, you're gone, basically. What he calculated is that even though these things are just a distortion in space and time, that's the description of them. So it's almost as if there's nothing there apart from a distortion in space and time. He calculated that they glow, so they have a temperature. So they emit radiation. It's called Hawking radiation. And so important was that discovery. If you go to Westminster Abbey in London, look on the floor of the Abbey on his memorial stone, and he's in there next to Newton and Shakespeare and all these people. And chiselled in stone on the floor of Westminster Abbey is his equation for the temperature of a black hole. So it was this tremendously important discovery. So he discovers these things glow, and he calculates how they glow. A very low temperature, but they emit things, which means that they shrink because they're emitting stuff. So that means they have a lifetime. So first of all, one day they'll be gone. So that means that you have to address this question of what happened to all the stuff that fell in. And his calculation said that there's no record at all of anything that fell in all this radiation that's come off the black hole. So it's purely information-less radiation. So what that means is that black holes destroy information, according to that calculation. And that's a big deal because nowhere else in all of physics does anything erase information from the universe. So it's really true that if I got this notepad and pen, right, and I wrote some things on it, and then I set fire to this, even just incinerated it, put it in a nuclear explosion, whatever, in principle, according to all the laws of nature that we know, if you collected everything that came off, all the radiation, all the bits of ashes and things, and you could just measure it all, then just in principle, the idea is you could reconstruct the information. So it all gets scrambled up and thrown out into, and so in practice you can't do it. But in principle, the laws of nature say that information is not destroyed. It's just scrambled up in a way that you can't reconstruct, right? But this calculation that Stephen did said there is no information in that radiation at all. Zero, just nothing. So it seemed that uniquely in the universe, black holes erase information. I should say it's very much in principle, this. So no one thinks in practice you could reconstruct what I wrote down on this if you set fire to it. But in principle, you could just collect everything. Then somewhere in that all that radiation and ashes and light that's come off the thing is the information. It's there. So you could reconstruct the book or what I wrote on this page in principle. But the thing about Stephen's calculation was that even in principle, it said there is no information. And by the way, it's kind of easy to see why, actually, because this radiation, this Hawking radiation that comes off the black hole, it's coming from the horizon of the black hole. So I should say what the horizon is, maybe. So remember I said that the sun, if you squashed it down within 3 kilometres of radius, you'd get this kind of distortion in space and time, from which if you went in across this region, 3 kilometres, you went inside it, you couldn't get out. So that's called the event horizon. So you wouldn't notice if you fell through the horizon of the black hole in the Milky Way galaxy. If you went into that one, we could be falling through that horizon now in this room, and we wouldn't notice anything, except that we couldn't get out again. And ultimately, in a few hours, in that case, time would end for us. So you go to the end of time. The sun will not form a black hole. When it runs out of nuclear fuel, it will collapse, and there's something that can stop it collapsing. It's beautiful calculation, by the way, that. You can do the calculation, it's great. So what stops it? There's something called a Pauli exclusion principle. The electrons don't want to be close together, roughly speaking, you could say it like that. So as you squash the thing, the electrons get closer together, and so they kind of separate away from each other and go into smaller and smaller little regions of space because they're trying to stay away from each other. But there's also something called the uncertainty principle, Heisenberg's uncertainty principle. So as you confine them into smaller regions, they start jiggling around faster and faster. And ultimately you can reach a limit where they're essentially trying to jiggle at the speed of light. And they can't. And so there's a limit to how much pressure that process can exert. And it turns out it's 1.4 times the mass of the sun, which is called the Chandrasekhar limit. So you can do that calculation. But it's a beautiful calculation because you could have worked that out not knowing that stars exist. All you need to know about is quantum mechanics and relativity. And you can make the calculation, what is the biggest lump of stuff that can be held up by this jiggling of electrons? It turns out it's 1.4 times the mass of the sun. Then you look into the sky and you see there are these things called white dwarfs, these collapsed stars, and there's none more massive than 1.4 times the mass of the sun. So it's very beautiful. And then you can get neutron stars, which are held up by the jiggling of neutrons. But ultimately, if you go to something that's three times the mass of the sun, something like that, a bit more, then nothing stops it collapsing. Yeah. And that's when you form a black hole. So the lightest black holes that we know of are around that mass, right? And then we know of them that are 10, 20, 30 times the mass of the sun from collapsed stars. And then these things, which are millions of times or even more the mass of the sun, which are the heart of galaxies. So these supermassive black holes, we could fall across this horizon it's just like being in empty space for us. So we would just be talking now, and we could have been talking on the outside of the horizon, and by the time I finished the sentence, we could be on the inside of the horizon, inside the black hole. And according to Einstein's theory, at least, which is the theory that predicted them initially, we could just do that. We could just go in, and we wouldn't notice for a bit. The thing we would notice ultimately is you go inexorably, nothing you can do, you go to this thing called the singularity once you've crossed the horizon. And you are going to that thing. And then the question arises, what is that thing? And one answer is we don't know. But in Einstein's theory, it's the end of time. So one way of picturing what's happened here is so distorted is space and time by the collapse of a star or the collapse of loads of stuff to make these big supermassive black holes. We don't quite know how they form, actually, but it's collapsing stuff. So it distorts space and time so much that in a real sense they kind of flip over. They get mixed up. And so this singularity, which you might have thought of as the point to which this thing collapsed, this infinitely dense point, you might think. But actually, it's more correctly to be seen as the end of time, because everything's got mixed up. So you go to the end of time. And it's just like saying, why can't I escape that thing? It's like, why can't we escape tomorrow? Right? So we are going to tomorrow. And if I said to you, let's run away from tomorrow, you'd go, you can draw a map of it. And it just literally, time ends, just purely in Einstein's theory. This is 1915. You just get a line there, a line that says, there's no future beyond this. It just stops. I mean, admittedly, that's not, we think there's a lot more to it than that. So we're starting to get hints about what might happen, which is leading us. So to backtrack a bit, why does this calculation Stephen did? Why has it got no information? Why does it say there's no information in this radiation? The thing is, it's coming from the horizon. So it's there's loads of ways to think about it, but one way is that this weird place, this point of no return in space that you can fall through, but it's a point of no return. It sort of shakes, it almost disrupts the vacuum of space and sort of almost shakes particles out of the vacuum. That's one way of thinking about it. But this radiation is coming from the vacuum. It's coming from empty space. Whereas if you think about the thing that I throw in, if I throw this notepad into the thing, then that goes to the singularity. It's got nothing to do. The radiation's got nothing to do with this thing. This thing's not. It's not set on fire or something like that. It's gone to the end of time, and just whatever's happened to it has happened to it. So this radiation's got nothing to do with anything that falls in at first sight, at least. And so that was the paradox. It's called the black hole information paradox. It's like, it's one way to put it is the laws of nature that we use to calculate what happens tell us that information is never destroyed. And when you calculate what happens, it tells us that information is destroyed. So that's why everyone got interested in it in the 80s, because it's interesting. One of the biggest details, it's not even a detail, it's one of the most shocking things about this, is I've described this, us falling into the black hole. And we're saying, in this room where we can't see out, what do we feel, what can we measure? And the answer is you can't measure anything, and we don't feel anything until we get inside and we approach the singularity for this one. But from the point of view of someone outside, the description is very different. So what would they see happening to us as we fall towards this thing? So even in Einstein's theory, with nothing else, no quantum mechanics or anything, then what they would see is time tick more slowly for us. Mm-hmm. So they would start to see, as we approach the black hole, if they could see our watches, if we were transmitting to them or whatever it is, transmitting from these cameras, we were sending it out to them, they would see our time tick more slowly, more slowly, more slowly. And they would see our time stop on the horizon. So they would never see us fall in. So from the point of view of someone outside, nothing goes into the black hole, ever. It would fade, but you could say this light is climbing away from through this gravitational field, so it's getting stretched. So we get redder and redder and redder, infinitely redshifted. Time passes more and more slowly until it stops on the horizon when viewed from the outside. From our perspective, we look at our watches, they go at 1 second per second. And that's absolutely central. So it's pure Einstein's theory. So that's the first thing to say. And it's a clue to the interesting things about what we're going to talk about, what follows, is that there are different perspectives on what's happening here. There's a perspective from our point of view, we're going in for a big black hole. From the point of view of someone outside, we never go in. And that's going to be kind of important for what follows. But there's nothing that's not described by Einstein's theory in that particular bit of the description. I mean, the first thing to say is we don't know, right? We can talk about the current research and speculation. We don't really have the tools to describe it. So a way to think about Einstein's theory is that, as I mentioned earlier, it really tells you how space and time are distorted. They also kind of get mixed up from the point of view of someone outside. So then you'll see that space and time are getting warped and distorted. And as I mentioned, they get so mixed up that on the horizon, you see that they flip. So the thing to bear in mind for all that follows with Einstein's theory is this very central idea that if you're freely falling through space or over space-time, if you like, then in the absence of these tidal effects, you really cannot tell that you're where you are in the universe. If you're close to a black hole, close to a big star, orbiting around a galaxy, just falling, whatever it is. So I think that's the key idea, this so-called equivalence principle. But of course, as we said before, the thing about a black hole is that why don't you see that? You could say, why don't I see these effects on the Earth? This distortion, this mixing. And you do. You see it in GPS satellites, for example. So if you think about what I said as you go closer to this thing, then as viewed from the outside, time passes more slowly. So you could say, well, why doesn't the Earth do that? And it does. So what you see is that time ticks at a different rate, by which I mean clocks tick at a different rate, atomic clocks or biological clocks. So you age at a different rate in orbit than you do on the surface of the Earth. And you're seeing this is the same effect. The reason it gets very extreme, I should say, it's quite a big effect for even near the Earth. So the drift is tens of thousands of nanoseconds per day. Time, a difference in the rate that time passes at the orbit of a GPS satellite and on the ground. There's tens of thousands of nanoseconds per day, even around the Earth. So the question of black hole really is, as you said before, if I could keep the mass of the Earth the same, but shrink it down to the size of a pea, then how does that distortion change as I go closer and closer to this immensely massive pea thing? And this is the effect, that time keeps going more and more slowly from the perspective of someone outside until you see it stop on the horizon, which, is, we said, for the Earth is around 1 centimetre, just a little bit less. So it's kind of not, in some ways, this behaviour of time is not unique to a black hole. It's just that in the black hole, it becomes extreme because the thing has completely collapsed. The distortion in space-time is not constant over the length of your body. So when we're falling in, we might as well be, this is the Einstein's equivalence principle in action, we might as well be in flat space, because the distortion, it's like saying on the surface of the Earth, if you look at a square mile of the surface of the Earth, you don't see the curvature, right? You have to go to bigger distances to see that you're on a curved surface. It's kind of like that. So the distortion, the difference in gravitational pull, as you said, or the distortion, you don't feel it until it becomes very distorted. Or there's a big gravitational pull when you get very close to this thing. And then you start to see that, and actually it works. It's not only stretching, it's also a squashing. So the way the tidal gravity works is to squash in one direction and pull in the other direction. So you start to feel this strange sort of sensation of being stretched and squashed. And as you go closer and closer to the singularity, those effects become much more extreme, until they're so extreme that, first of all, you cease to stay together, and then the atoms get separated. And then the protons, the quarks inside the protons will get separated. And ultimately, according to Einstein's theory, the tidal forces become infinite. So formally infinite. And so everything has gone. Everything's been ripped apart. And this is what we call the singularity. So the whole thing kind of gets very extreme and breaks down ultimately in Einstein's picture. The other thing we've had is so-called gravitational wave detections. So these are colliding black holes, and they collide and merge together. And obviously that's quite a violent event in the universe. And so that event, that process ripples space-time. So it sends ripples out in the fabric of the universe, space and time. And actually Kip Thorne, I've spoken to him several times. He's one of the greats, right? Won the Nobel Prize for this. And he calls it a storm in time. So you get a time storm. So really, we're to think, as we speak now, there will be these very tiny ripples from violent cosmic events passing through this room. And they're changing the rate that time passes. So that as they go through. And we can detect that now. So we have detectors that can pick that up. And so we've seen those collisions as well. Another way to think about it is that there's a beautiful model, which is my favorite model. It's called the river model of a black hole. You can write the equations as the space being like a river that flows into this thing, almost like a sinkhole or something in space. And the river of space flows at the speed of light inwards on the horizon. And then faster than light inside. So if you imagine that you're a photon, a particle of light, you're like a little fish swimming against the tide. But if the tide's going at the speed of, as fast as you can swim, the speed of light, you can't get out. Not only can you not get out, but you're going inwards towards something. And this thing, the something, is called the singularity. You say, what is this thing, the singularity? And I think it's really tempting to picture it as some infinitely dense point to which this star collapsed. When you draw a map of space and time, what you see really clearly is that this singularity thing is not a place in space, it's a moment in time. And it's in fact the end of time in Einstein's theory. So a way that I often kind of picture it or explain it to myself is that space and time have become so distorted that when you look at it from the outside, they flip roles. So space has become time, and time has become space. So the answer is, according to Einstein's theory, no, because you've gone to the end of time, right? And there's no way. Basically, Einstein would say it's all over. You've got ripped to bits. Everything has got ripped to bits. You've gone to this infinitely distorted space and time, and it's just done. Well, Stephen Hawking initially would have said in the 1970s, what did Stephen Hawking discover in the 1970s? So in his words, he discovered that black holes ain't so black. So we've said nothing comes out of a black hole. Everything that goes in goes to the singularity, it's gone forever, because the black hole lives forever. Now, Stephen Hawking calculated that if you do some essentially quantum mechanics, right, around the horizon of the black hole, so you think about what happens, what does a black hole do? A way of thinking about this is that in quantum mechanics, which means in reality, in nature, empty space isn't empty. It has a rich structure. So the vacuum of space has a structure. And the black hole, you might say, well, this strange behavior of space and time, it must do something. And it does. It disrupts that structure. And the result is that particle photons, essentially, but what's called Hawking radiation, is emitted from the black hole. So the result, and there are different ways of thinking about what's happening. There's the very precise way. Stephen Hawking gave an analogy in his paper, and he said it's just an analogy, and people get very worked up online when you talk about his analogy, but Stephen did write it down, right? So a way to picture the quantum vacuum is that you can imagine particles coming in and out of existence all the time in the vacuum. So in accord with the uncertainty principle, they come in and out like that. You can kind of picture it like that. I emphasize it's not supposed to be a technical description, but you can picture. So you can picture these in the vicinity of the horizon. You can picture that this structure gets disrupted. You could have the situation where one of these particles is on the inside and one is on the outside. And then we know what's happening to the one on the inside. It's going to the singularity because we said the river of space is going fast in there, or whatever, whichever way you want to think about it. So the other one is basically made real and escapes. So that's a picture that Stephen himself gave. But the upshot is very accurate. The point is that this particle has been shaken out of the vacuum. And it's now a real particle when viewed from the outside, and it goes away. So that what is that? What particle's been emitted? It's a temperature. It's glowing. And so that means it's losing energy. And so that means it has a lifetime. So over time, and these are enormous times, far greater than the current age of the universe for any black hole that we know of in the universe, because we don't know of tiny ones. So all the ones we know of, the immense lifetimes, in excess of 10 to the power 100 years for these supermassive ones, right? Ridiculous times. But ultimately, they have a lifetime. And that means one day it will be gone and space will be all nice and normal again, right? All you will have left will be the Hawking radiation that's been emitted over these eons of time. So the singularity inside a black hole in Einstein's theory is the end of time. And in Einstein's theory alone of the evolution of the universe, there is another singularity at the other end of time, which is the Big Bang singularity, which you might be tempted to call the beginning of time. It's a very different singularity. Black holes are maximally scrambled information, right? The highest entropy things we know of in the universe. And one of the great mysteries about the origin of the universe is it's a very low entropy state. Broadly speaking, you can, if you want to know more about that, Sean Carroll actually writes a lot about this. So there's a lot of interesting stuff to say. But it's a different kind of singularity. And so, are they related, is the question. I would say, yeah, our understanding of them surely is. But it's really not clear. And when you add quantum mechanics in, then you begin to ask questions about whether the Big Bang, if there is such a thing as a singularity in the past, is it what is it? Is it the beginning of time? There's a thing called the no boundary idea that Hawking and others had, and again, all bets are off, right? But I think it would be good. I think not would be good. It is correct to say that I'm sure the understanding of the two is related, but we understand neither at the moment. There's a thing which is really important called the firewall paradox, as it was initially introduced. And it hasn't been resolved yet. And the problem is, when you disrupt space in this way that the black hole does, and when you try to understand what's happening to the information and entangled particles that are on one side of the horizon and the other side, the Hawking radiation that we discussed earlier, you do bump up against a problem, which is that maybe this description of the equivalence principle and of us freely falling across the horizon from our perspective into the interior of the black hole, maybe that doesn't quite stand up. So maybe you're getting a challenge to this basis of general relativity. Maybe it's really true that actually there isn't an interior. And maybe it's really true that you don't go in. There isn't an in, right? And so it's you'll see if you go and search through the literature that the firewall paradox was that these papers were big papers in this debate. And then some people thought they were solved, and other people thought they weren't solved. And I think it's fair to say that the jury is still out on these issues. But what the thing to emphasize is there's something really fundamental going on here. And it almost certainly is associated with the nature of space and time themselves, or space-time. It's associated with geometries of space-time, maybe wormholes, maybe those kind of things. So it's tremendously interesting. And you'll see, it's just wonderful to dig into this subject because it's it develops so fast, and our understanding is developing so fast. But the last thing to say is it does look like that there is a description of the universe that looks like a giant quantum computer in some sense, which does not imply that someone built it. But it does suggest that there's a good description of reality that you can write down in the form of some kind of network of entangled qubits, which are presumably the Planck length inside. I mean, who knows? Maybe even that's not obvious, right? But something like that. So the techniques that you develop as let's say a PhD student or a postdoc or someone who's working in this area, the techniques that you develop to try to understand what the black hole is doing are the same techniques you need if you want to understand how quantum computers work. So, and that's a real engineering question as well as a fundamental physics question. We're trying to build these things. We haven't built one that works in the way we want to yet, But obviously, Google and Microsoft and IBM and others are pouring a lot of money into it because they're profoundly powerful devices. But the insight, a lot of insight now into how they might work and how we might build them is coming from this field of emergent space-time. So it's the best example I know of, if you say to a funding agency, I want money to work on black holes. They go, what is it any use? I mean, what the point, a black hole, does anybody care? The lesson is that when you study nature and you go to you try to study things that you don't understand, that pose profound questions about our understanding of physics in this case, then you are, I would say, likely to learn something useful because you're studying reality. And this is the best example of that I know, because you're studying completely collapsed stars or the things at the hearts of galaxies, and you're gaining insight into quantum computers and networks of qubits and quantum information. It's the most wonderful thing.